grounds. Ocean tornado on the ground.
Destructive tornado was located over Kokomo. Tornado emergency for Kokomo.
It all happened during one afternoon. One afternoon of unrelenting chaos, which would mark its place in both weather history and local legend. Over 6 hours, 24 tornadoes would tear across Indiana, Ohio, and Ontario, Canada in an unusually focused and intense outbreak. An outbreak that nobody saw coming. Now, 10 years after this event darkened the Indiana skies, I'm headed back out to where it all happened. In this video, we'll find out what factors came together to produce this outbreak and retrace the path of the day's most infamous tornado. We'll look back at the environment, the storms,
Debris falling from the sky,
and the aftermath.
A tornado emergency.
10 years after Dark Wednesday. To understand what made August 24th, 2016 so unusual and destructive, we need to know what was going on in the atmosphere. The August 24th outbreak was associated with a feature known as a remnant mesoscale convective vortex, or MCV. During the summertime, large thunderstorm clusters can become so organized that, through a combination of wind shear and the Coriolis effect, a vortex develops within the complex. This is the MCV. A vortex is a stable structure, so even after the thunderstorms weaken overnight, the remnant MCV can persist. This area of low pressure then drifts with the mean wind, potentially acting as a trigger for more severe weather downstream. Remnant MCV tornado outbreaks are a periodic occurrence in the Midwest. In fact, such an outbreak occurred over southern Illinois and Indiana just 2 months ago. Although these types of outbreaks have been known to occur over the years, it wasn't until research was published by Cameron Nixon that we really came to understand how they work. As a matter of fact, his 2016 study, an investigation of surprise tornado events associated with remnant mesoscale convective vortices, specifically references the August 2016 outbreak. Through a study of MCV outbreaks from 2006 to 2017, Nixon found several characteristics of their environments that could support tornadoes. MCVs often move into a very warm and moist environment, which leads to large values of low-level CAPE. Large low-level CAPE can produce stronger buoyant accelerations in the lower part of a thunderstorm updraft, which can aid in the vorticity stretching process. Because of the moist boundary layer conditions found in MCV environments, LCL heights are often rather low. This can make successful tornado genesis more likely because of the close proximity of the base to the ground, and rear flank downdraft air is usually warmer than it would be in a higher LCL environment. Since the remnant MCV is a small center of low pressure, it can augment the low-level wind profile by creating backed surface winds. When coupled with increased mid-level winds from the original complex, this can create enhanced low-level wind shear and SRH, increasing the potential for supercells and tornadoes. Because of the generally modest large-scale flow, remnant MCV environments are often characterized by weaker storm-relative winds than with larger, more dynamic storm systems. Weaker storm-relative winds, along with low LCL heights, can support a narrower updraft diameter in supercells. This can create an environment conducive to miniature supercells, which are rotating thunderstorms with a smaller mesocyclone than typically found in supercells. Despite their name and smaller size, many supercells can still produce serious hazards. They have been hypothesized to tilt streamwise vorticity more efficiently than larger supercells. Peters et al. 2022 describes how supercells with weaker storm-relative wind have streamwise vorticity trajectories that travel a shorter horizontal distance, compared to ones with stronger storm-relative winds for an equal vertical displacement. In other words, the steeper slant angle of vorticity tilting in many supercells can allow for a higher efficiency of vorticity tilting into the vertical, creating strong low-level mesocyclones. This is especially true in environments of large CAPE, low LCLs, and enhanced wind shear in the low levels, as discussed by Nixon. This can make many supercells efficient tornado producers. Nixon's research also identifies features in the synoptic scale pattern that are often associated with remnant MCV events. These include weak or split flow aloft, upper-level ridging conditions, and/or significant severe storms upstream. This is important to understand where the MCV originated and how it tracked into Indiana and Ohio. With these concepts in mind, we can start to piece together the specific characteristics of the 2016 outbreak and uncover what made it so significant. The MCV responsible for the outbreak was born out of a mesoscale convective complex originating from the northern plains and Midwest, specifically western Iowa. This is where a thunderstorm cluster organized and produced some reports of damaging winds, as a mid-level circulation became established. Two new clusters of storms would develop ahead of the remnant MCV by late morning, one moving out of central Illinois, which would decay in Indiana, and another in northeastern Illinois, which would eventually produce the first round of tornadic supercells. Surface observations confirmed rising temperatures in the region despite the early rain, showing that this activity had a negligible impact on daytime instability. Cloudy skies ahead of the MCV also demonstrate the enhanced lifting that it introduced, which, in this moist environment, helps to explain the abundance of precipitation during the early day. By 17Z, the circulation induced by the remnant MCV was apparent over northern Illinois in visible satellite imagery, and it was moving roughly due eastward. Cameron Nixon's research showed that the majority of tornadoes associated with remnant MCVs occur in its right front quadrant, following the motion. This is a similar pattern which is observed with tropical cyclone-induced tornadoes. The position and motion of the remnant MCV placed northern Indiana and Ohio firmly within this right front quadrant. Although temperature lapse rates were modest, very warm and moist low levels allowed for appreciable destabilization through the afternoon. Weak inhibition at 12Z probably contributed to the initial weakening of thunderstorms, but warming and moisture advection would allow for destabilization as temperatures came up into the low 80s. With dew points rising into the mid-70s, this not only promoted a deep layer of instability that included low levels, but also lowered LCL heights to less than 500 meters, creating extremely low cloud bases. Wind shear was enhanced ahead of the MCV, especially in low levels, and would provide the key mechanism for storm organization into supercells. Although 12Z upper air observations showed 850 millibar winds of around 20 to 25 knots over Indiana, by 21Z, archive mesoanalysis shows winds increasing to 40 knots. And as surface winds remained generally out of the south, 850 millibar winds veered with time to create a more strongly curved wind profile. These factors increased both speed and directional shear in the lowest few kilometers of the atmosphere over Indiana and Ohio, increasing 0 to 3 kilometer SRH to values above 200 meters squared per second squared. This is a value typically considered favorable for tornadoes in supercells. Supercells were favored not only because of the low-level shear, but also wind shear through a deep layer. At the base of the weak mid-level wave associated with the initial complex, enhanced 500 millibar winds allowed for values of effective bulk wind difference, also called effective bulk shear, as high as 30 to 35 knots over Indiana and Ohio. This is also a range traditionally considered favorable for supercells, especially within an increasingly unstable air mass. Observed soundings taken from southwestern Ohio during the morning and evening of August 24th demonstrate how the environment was changing. Although this location was removed from the area of the tornado outbreak, it sheds some light on how the atmosphere was changing regionally. At 12Z, the ILN sounding showed a moist but stable air mass over the region. MU SIN was around negative 100 joules per kilogram, with a positive theta E lapse rate below 900 millibars, and no measured 0 to 3 kilometer mixed layer cape. Interestingly, there was already some wind shear in place, as southeast surface winds veered to westerly aloft. However, flow was weak overall. But things changed dramatically by 0Z. A deep positive area was noted on the SKU-T profile as moisture advection and cloud cover had retained a moist boundary layer. Surface-based CAPE now exceeded 2,300 joules per kilogram, and the surface-based calculation seems appropriate given the absence of a well-mixed PBL profile. LCL heights for this parcel were below 500 meters, and the wind shear profile was also more impressive than the morning sounding had shown. As directional shear was maintained, the amplified low-level flow created a large, looping hodograph profile in the lowest few kilometers, translating to 0 to 3 kilometer SRH values around 350 meters squared per second squared. 0 to 1 kilometer storm relative winds of 27 knots were likely a bit weaker to the west and favored smaller updraft diameters, which could more efficiently tilt the highly streamwise vorticity indicated in the 0 to 500 meter hodograph segment. Deep layer wind shear was only marginally supportive of organized storms, but given the importance of low-level shear on supercell formation, abundant instability, and stronger mid-level flow to the northwest, a discrete supercellular mode resulted. ChaseArchive.com, an expansion of Cameron Nixon and Kyle Gillette's case archive from UStornadoes.com, provides a RAP model-based sounding for around the time of the Kokomo EF3. Although this information is model-derived, it reveals several important characteristics of the environment which made it such a prolific tornado producer. Surface-based 0 to 3 kilometer CAPE over 150 joules per kilogram, and overall SB CAPE above 2,000 joules per kilogram work to create powerful buoyant accelerations in updrafts. A strongly veering vertical wind profile created ample wind shear, including 0 to 3 kilometer SRH around 250 meters squared per second squared, and effective bulk shear around 40 knots. 0 to 1 kilometer storm relative wind of 22 knots favored many supercells, which effectively tilted vorticity that was 99% streamwise in the lowest 1 kilometer. It was a potent set of ingredients for supercells and a recipe for a tornado outbreak. The tornado outbreak of August 24, 2016 began as supercells evolved out of the second cluster. This unassuming band of convection stretched from near Winnemac, Indiana to Danville, Illinois at around 17Z. Portions of the line strengthened by 18Z as individual cells began to organize out of the cluster. The most notable one was west of Crawfordsville, but another was slowly coming together northeast of Lafayette. At 2:38 p.m., the first tornado of the outbreak touched down southeast of Crawfordsville, Indiana. It produced EF2 damage in the Lindsborg area, but as this occurred, another supercell was taking shape to the north. A well-defined hook echo became apparent over southern Carroll County. Inflow intensified, and as the mesocyclone grew stronger, a tornado warning was issued for Kokomo, Indiana. We got into position on the south side of Kokomo, gazing at an initially unimpressive sky. But as the supercell entered Howard County, an incredible uptick in lightning occurred, and soon, the most menacing sky I've ever seen took form. Violent bolts of lightning came crashing down as a well-defined wall cloud became visible. What follows is my personal encounter with this fearsome tornado, and a retracing of its entire path 10 years later. The tornado began at about 3:20 p.m. near this intersection behind me. Already showing multi-vortex structure, it immediately began producing EF2 damage. From my position, the wall cloud was becoming even more defined, creating strong inflow and presenting a well-defined rear-flank downdraft clear slot. The tornado fluctuated in intensity during the early stages of its progress, but it quickly intensified as it impacted the Park Place apartments. The tornado produced its first EF3 damage in this area, and the Park Place apartments took a direct hit. And from there, Highland Park was next. Back south, we were monitoring the wall cloud when, just above the tree line, rapid cloud motion became visible. The tornado had come into view.
Should be crossing Dixon right now, the area of Boulevard. We have damage at Howard Haven, West Home.
Oh my gosh.
What we witnessed was a truly mesmerizing display of nature's power. Captivating, terrifying, and surreal. We watched the intense rotation churn clouds into a chaotic swirl of motion, a cloud of debris encircling the tornado and being ejected in front of it, as the Park Place apartments were hit.
Kilo 9 Charlie Romeo Hotel.
Oh my gosh.
Maintaining its status as a strong tornado, the vortex swept through Highland Park. Even to this day, open skies are visible where tall trees once stood. The park suffered extensive tree damage, which rendered the area impassable in the storm's immediate aftermath. It wouldn't be until 2 weeks after the storm that I was able to make it out to the park, standing amid the destruction of a landscape I'd loved since childhood. But the tornado was only getting stronger as it drew deeper into Kokomo. The once fragmented funnel had condensed into a steady cone, indicating a drop in central pressure. The vortex was about to inflict its most severe damage. The tornado produced significant damage as it crossed portions of 17th Street, damaging or destroying many homes in this populated part of town. As the intense tornado barreled through town, the National Weather Service upgraded our tornado warning to the highest possible level: tornado emergency.
A confirmed large and destructive tornado is located over Kokomo, moving east at 30 miles per hour. Tornado emergency for Kokomo.
It was in this area that we assisted with early search and rescue operations. It was a defining moment in my life, intensely sobering to see damage left only minutes after the tornado had passed. We checked on residents and tried to remove debris from the roadway. Thankfully, we didn't encounter any serious injuries. But the most intense and memorable damage of this tornado occurred right here in the Markland Mall parking lot. It was right here that the tornado infamously blew down a Starbucks building. As you can see here, it has been rebuilt since this occurred, but wind speeds were estimated at this location at 152 miles per hour, marking the peak of the tornado's intensity. Although a new building has been established, residents in the area still remember what it looked like in the moments after the tornado.
Starbucks is completely gone.
Heading east, the tornado would tear through the Cedar Crest neighborhood, destroying several homes as it remained a strong tornado. A conspicuous lack of trees marks the tornado's path as it ripped through the Cedar Crest neighborhood. The normally quiet residential area took the brunt of winds exceeding 120 miles per hour, tearing apart trees, ripping roofs from homes, shattering windows, and leaving residents shocked at the storm's fury. By this point, the tornado had become obscured by RFD rain curtains from our angle, but was still lofting debris from the Markland Mall vicinity. At 3:34 p.m., after carving a path of destruction nearly 9 miles long, the tornado finally ended here, on the north side of Kokomo Waterworks Reservoir No. 2. The tornado weakened substantially before lifting, but the damage had been done, and the storm had left its mark in tornado history. But the tornado outbreak of August 24, 2016 was far from over. With conditions still favorable for tornadic supercells, a new round of storms initiated along a zone of convergence in north-central Indiana, aided by lift from the MCV. Over the course of that evening, Howard County, Indiana would become the epicenter of this incredible event. The longest-lived tornado of the event occurred from a supercell which came out of Carroll County.
That's it.
The storm presented amazing supercell structure, and the EF1 tornado it produced was on the ground for over 40 minutes. We raced south ahead of a new tornadic supercell and would soon see the best supercell structure I've ever witnessed.
Look at this man though.
The towering mesocyclone stood over a fearful town, and a rapidly rotating wall cloud hung beneath it. It was clear that this incredible supercell was about to produce yet another tornado. Positioning ahead of the cell, inflow ripped into the storm as we sat directly in the path of its low-hanging wall cloud.
Touching the ground. Again, I repeat, I don't see anything touching the ground. I see a lot of rain shafts, and I see some shit beginning to form.
The rear flank downdraft swept in, and at 6:58 p.m., a slender tornado touched down in the Indian Heights neighborhood.
Tornado was on the ground. Wow.
I'm aiming it down. That's a height.
But as one cell passed by, still another came in, as we maintained our position in the forward flank of another tornadic supercell.
Yep.
We were able to get a brief view of this tornado through heavy rain, and as it passed by, we witnessed one more unusual sight of the day. Amid heavy rain, twisted vegetation debris began falling from the sky around us. It was another surreal moment and a remarkable day. Finally, as the sun began to dip below the horizon, the tornado outbreak came to a close. After hours of unrelenting chaos, the residents of Howard County, Indiana, as well as several other communities, are finally free of nature's wrath. The outbreak was over, but the recovery had only just begun. In the aftermath of the August 24, 2016 tornado outbreak, one question was on everyone's mind. How did such an active tornado event come without warning? In his work, Cameron Nixon points out the reduced predictability that comes with remnant MCV tornado events. Most MCVs don't produce tornado outbreaks, and generally only a handful of MCV tornado outbreaks occur in the Midwest every year. This makes real-time analysis critical for anticipating when and where these tornadoes might occur. 10 years ago, extensive soundings were only conducted from certain National Weather Service offices, a situation which hasn't improved today. Although numerical forecast models have improved some since then, and direct observations can be made in various ways, smaller scale weather features can still lower forecast confidence. The sparse nature of observations was key to underforecasting this outbreak, as these observations are fed into numerical weather prediction models to improve the accuracy of their output with each new run. For real-world analysis, the downscale transition from linear clusters to supercells is an unusual occurrence, and would have been difficult for forecasters to anticipate. It's because of work by people like Cameron Nixon that our understanding of remnant MCV tornado events has improved in the intervening decade. With lessons learned from this event, predictability has improved. But August 24, 2016 leaves us with an important lesson. Tornado outbreaks can still exceed forecast expectations and come with little warning. In all, 24 tornadoes occurred in Indiana, Ohio, and Ontario. The strongest tornado of the day occurred near Woodburn, Indiana, and was nearly of EF4 intensity. Nixon's 2019 research also highlights the unusual magnitude of this outbreak. In his period of study, he found that only 5.3% of MCV tornado events had over 10 tornadoes. He also found that only 2.3% of MCV tornadoes are rated EF3+. On August 24th, that was 8.3% of tornadoes. The tornadoes caused over $100 million in damage and injured nearly 24 people. But by a miracle of God, no deaths occurred. For Kokomo, Indiana, it was the strongest tornado to hit town since 1965 and came only 3 years after double EF2 tornadoes ripped through the same area. Most of the injuries from the outbreak occurred here, with 1,000 homes damaged and 80 destroyed. It caused roughly $10 million in damage, another scar in a community with a long history of tornadic impacts. August 24, 2016 remains an important date for many people, including me. This was the location from which I watched the tornado, 10 years ago, in this very spot. 10 years ago, that horizon was dominated by one of the most violent forces of nature. And I still think about it today. It was a moment in time that redefined my view of severe weather. It was a pivotal day in my early storm chasing career. And it was a day that would change me forever.